Today's topic is 8085 Microprocessor Architecture. So before going to this topic, we can see the features of 8085. So 8085 is an 8-bit general purpose processor. Then it needs only 5-volt power supply for its operation. So it is a 40-pin dual line package single integrated circuit. It can operate with a 3 MHz clock frequency. The width of the data bus is 8-bit, then width of the address bus is 16-bit. 64 kilobytes of memory locations can be accessed directly by the 8085. So 8085 has one non-maskable interrupt. So non-maskable means it cannot be disabled or ignored by the instructions of the CPU. And then 3 maskable interrupts, RST 7.5, 6.5 and then 5.5. So maskable interrupt means it can be disabled or ignored by the instructions of the CPU. So these are the features of 8085. So now we can see the architectures of the 8085. So what are the blocks available in the 8085 architecture? This is the 8085 microprocessor architecture. Here 12 blocks are available. So the first one is the accumulator, second one temporary register, the third one flag register, then fourth one ALU, then fifth one instruction register, sixth one instruction decode and machine encoding, then seventh one registers, eighth one address buffer, ninth one data/address buffer, 10th one timing and control, 11th one interrupt control and then 12th one serial IO control. So these are the main 12 blocks available in the 8085 microprocessor architecture. So let us see one by one. So the first one, accumulator. So accumulator is nothing but it is an 8-bit register. It holds the one of the data to be processed by the ALU. So it also stores the results of the operation. The accumulator is also called as A register. So accumulator or A register. So accumulator is connected to the 8-bit internal bus. So this is the internal bus 8-bit. Here we are giving the two bidirectional. So bidirectional means you can send or receive the data from this internal bus. So this is the internal bus. So this is the bidirectional bus is given. So you can transmit or receive the data. The two-state output of the accumulator drives the ALU. So this is the arithmetic and logic unit. So one input from the accumulator is given to the ALU. So next, this one is the temporary register. So the temporary register is nothing but this block 7. So see here 8 temporary registers are available. W register, Z register, then B register, C register, D register, E register, H register and then L registers. So the combinations of the two 8-bit registers can be employed. The combination of the two 8-bit registers is also known as register pair. Register pair. So the register pairs, it may be, you can combine these two B and C. So B, C register pair, then D, E register pair, then H, L register pair. Like this, we can use the two register pairs 8-bit and 8-bit. So we can form the 16-bit data. So next we will move on to the program counter, that is PC. PC is nothing but program counter. So it is a 16-bit special purpose register. It is used to hold the memory address of the next instruction to be executed. So it keeps the track of the memory addresses of the instructions in a program while they are being executed. So the microprocessor increments the content of the program counter during the execution of an instruction so that it points to the address of the next instruction in the program at the end of the execution of the instruction. So this one is the 16-bit register and stack pointer also 16-bit register. So next we will move on to another 16-bit register, SP. SP is nothing but stack pointer. The stack pointer is a 16-bit register used as a memory pointer. So it maintains the address of the last byte entered into the stack. That is, the stack is the portion of the RAM. So the stack pointer is decremented each time when data is loaded into the stack and is incremented when data is retrieved from the stack. So these are the registers available in the 8085 microprocessor. So once again we will see the temporary register. So this one block 2 is the temporary register. So in the temporary register it may be either B register, C register, D register, E register or H register and L registers. So if you want to give the input as 16-bit means we can combine the B and C register. That is called the register pair, BC register pair, DE register pair and HL register pair. Then PC is nothing but program counter. It is a 16-bit register used to store the address of the next location. Then SP is nothing but stack pointer. It is also 16-bit register used as a memory pointer. So next we will move on to the ALU. So ALU is nothing but arithmetic and logic operations. It can be performed with the 8-bit data. The contents of the accumulator. So this is the first content, accumulator, and the temporary register. This is the second content, temporary register, are the inputs to the ALU. So it can perform arithmetic operations such as addition, then subtraction, and then logical operations such as AND operation, then OR operation, then XOR operation. So these operations can be performed with this ALU. The ALU result is then stored back into the accumulator. Again, this output of the ALU is stored in the first block accumulator. So next, this one is the flag register. So the flag registers, we can see the one diagram, flag register. So this is the flag register. So the flag register, it is then 8-bit flag register. So here it is a group of 5 individual flip-flops. So it holds data during an arithmetic and logical operation. So it is used by the microprocessor. So see here, the content of the flag register will change either 0 or 1 after the execution of the arithmetic and logical operations. So there are 5 flags are available. First one is this one is the first one, carry flag. Second one, parity flag. Then third one, auxiliary flag. Fourth one, zero flag. And then fifth one, sign flag. So 5 flags are available. So if the output of the ALU is 0, if it is 0 means there will be no carry. So this flag cannot be set. Then if the result is 1 means carry flag can be set in the flag register, this flag register. Then in the D2 bit it is parity flag. So if the result of the ALU is 0 means then odd parity is set, and then if the result is 1 means even parity is set. Then auxiliary flag is nothing but the overflow of the D3 bit, this D3 bit. If the result of the ALU is overflow means then auxiliary flag will be set. If it is 0 means no auxiliary flag set, and if it is 1 means auxiliary flag set. Then D6 0 flag. So 0 flag means the result of the ALU is 0 means result not 0. Then if it is 1 means the 0 flag can be set. Finally the fifth one, sign flag. So sign flag means the output of the ALU is 0 means then it is a positive, and it is 1 means it is a negative. So these are the flags available in the flag register. So depends upon the ALU operations, you have to mention the flag. Next one, instruction register. Fifth block is the instruction register. So instruction register is an 8-bit register. When an instruction is fetched from memory, it is loaded in the instruction register. The instruction decoder, next it is moved to the instruction decoder, 6th block. Instruction decoder decodes the contents of the instruction register. It also determines the operations to be followed in the executing the entire instruction and directs the timing and control unit accordingly. So this is the instruction register and instruction decodes. Finally it is given to the timing and control unit. Then this one is the 8th one is the address buffer. So address buffer is address is 16-bit and then data buffer is 8-bit. So see here it is multiplex AD0 to AD7. So that means address as well as data bus. So 0 to 7 and then here it is 8 to 15. So from this microprocessor can send the address or data to the memory or input output devices. So next here it is the serial IO control. So serial IO control is nothing but we can receive the serial input data. So serial input data enters 8085 through the pin is called the SID, that is serial input data. Then SOD means serial output data. So it leaves, the output leaves through the SOD, serial output data. So two instructions known as SIM and RIM allows us to perform the serial parallel conversion needed for the serial IO devices. So this serial IO control can be used for the serial communication. Next, this one is the interrupt control. So there are 5 interrupts available in the 8085 microprocessor. INTR, then RST 7.5, RST 6.5, RST 7.5 and then trap. So trap is nothing but non-maskable interrupt. This one is non-maskable interrupt. So non-maskable interrupt means it cannot be disabled or ignored by the instructions of the CPU. Remaining 4 are the maskable interrupt. So then we have to acknowledge whether the interrupt the CPU is ready or not through this INTA. So INTA is nothing but interrupt acknowledgement. So that's why we are giving the acknowledgement. We have to put the arrow mark in the outward direction. Remainings are the inward direction to the interrupt control. Then the last block is the timing and control. So the timing and control, here many pins are available. So here see here, this one is the reset out and then reset in. These are the control signal. Then HLDA and then hold signal. So hold is used for the DMA purpose, direct memory access. So when we are giving the hold signal means we have to get the acknowledgement. So that's why this outward direction is the hold acknowledgement. That is HLDA, hold acknowledgement. Then this one is IO/M bar. Then S0, S1. So these 3 are the status signal. Whether we are getting the data from input devices or the memory devices, like that we can check. Then ALE. ALE is nothing but address latch enable. So here we are using the address and data bus. So we have to demultiplex. So that's why here we are using the status signal address latch enable. The next one, write signal, whether we want to write the data into the memory or read the data into the memory or from the memory. So like that we can give the status signal. Then ready signal. So ready is nothing but when the CPU is ready or not, like that we have to give the input to the timing and control. According to the timing and control, we can process the data. Then next one is the clock output. So here two clock frequencies. This is the oscillator, and the oscillator generates the two-phase clock signals that synchronizes all the registers. The controller sequencer also produces the control signals needed for the internal and the external control. So the timing and control signal section of the microprocessor includes the oscillator and the controller sequential. So here X1 and X2, that is 3 MHz clock frequency can be generated. According to the clock frequency, it processes the data and gives the output. So this is the overview of the 8085 microprocessor architecture. So next class we can see about the addressing modes of the 8085 microprocessor.